we are here to give you a tutorial on synthesis of a particular kind. What is synthesis? The problem is easy to state. You want to write a program or find a program, P, that meets some specification, which you can write in many ways. One of them is to get a predicate over inputs and outputs, which tests whether an output is correct with respect to the input of the program. So whether the output has been computed correctly. So the logical formula, the constraints, are you looking for a program P such that for all inputs that program computes the correct value. Okay. When would you like to use synthesis? Well, there are several situations. One of them is productivity, when you may want to write that specification phi faster than the program itself. And in some cases, correctness, when proving phi or convincing yourself that specification is correct is faster than proving program P. In this tutorial, for reasons that will become clear sooner, we'll focus more on productivity than correctness, although correctness still under certain circumstances can be guaranteed as well. What is this tutorial about? Well, we do not want to teach you how to use a particular synthesis tool. Right? You can look at the PLDI tutorial of Armando Solar Lezama for that. So we will not teach you much about programming with synthesizers. We will, however, give you a recipe for building a lightweight synthesizer yourself. So if you have a particular task, such as synthesis of biological models, we'll show you how you could design a small domain-specific language, write an interpreter or synthesizer for it in 2 months or a semester. We'll talk about the concepts and algorithms beyond solving the exists P for all inputs problem. So how to solve this second-order formula, and how to write specifications as well, because that turns out to be equally hard. And finally, we'll talk about how to make synthesis more general, in the sense of, well, if we can think of everything as programs, then we can then synthesize with program synthesis, formulas, compilers, and so on and so on. Why this might be interesting to you, we were trying to judge who the audience might be for this tutorial. And so if you are a researcher in solvers or decision procedures, you'll see that program synthesis is another application for your solvers. And also internally for your solver, synthesis might help building better solvers. The synthesis might infer inductive invariance, come up with efficient encodings of problems into your logics, and so on. If you work in controller synthesis, we hope to inspire phrasing controller synthesis as a particular kind of constraint solving problem. And if you are in software model checking, at what you will see, we do nothing more than lift your techniques in software model checking into the domain of synthesis. And you'll see that the solver-based synthesis that we present is to sort of classical synthesis what model checking is to classical verification. And so whatever you know how to do, you can probably apply in this new setting as well. We'll start by picking at classical synthesis to see what we do differently and how. There are at least 2 branches of classical synthesis. One of them is the controller synthesis, usually phrased as automata-based technique. This is perhaps more from the CAV world. And we will not talk about that, but you can look at the talk that Madhu gave 2 days ago at the synthesis workshop. The classical synthesis for us is mostly the synthesis of programs that are functional, that accept input, produce an output, work on rich data types. And that is coming more from the PLDI POPL world, and it classically has been done in the deductive setting. So we will examine how that works on a really simple synthesizer that is, however, really nice. The synthesizer is called Denali, and the problem is to accept a specification like this, which you could view as straight line sequence of instructions. So a small instruction sequence, and the goal is to compute a more efficient instruction sequence. So essentially, instruction level optimization. Okay? So this requires 2 instructions, and the system starts with building a tree, abstract syntax tree for the computation. So register is multiplied by 4, and then you add 1. Okay? And so what then it does, it looks at the knowledge of axioms of the system, and there is an axiom which says that a number that is a power of 2 can be expressed in the following tree. And so it creates this tree, and it says that this node and that node are equivalent. Okay? Then it looks at this tree and looks at another axiom that it knows, and this defines this instruction and says, okay, if I need to compute k times a number that is a power of 2, I can express it with this computation, with this instruction, and it's done that. Okay, so here is now another equivalence that we have found between this tree and that tree. Okay, and the reason why we were able to find this equivalence is that we have previously discovered that. Okay. And then we look at another axiom which tells us that this special instruction can be computed, can compute k times 4 plus some number n. Okay, so we found another equivalence, and this subtree here, okay, happens to be equivalent to the original specification, right? So we have found equivalence of the original spec rooted here and a new instruction, and this gives us a really fast way of computing the original problem in one instruction, in fact. So what we have done here, based on the knowledge of the axioms, we have built, well, not quite all, but you can think of in the limit all equivalent programs by finding equivalences over trees, and that gave us a space of programs, and everything equivalent with the root of the original problem is now a synthesized program. Okay. So what is interesting is to see what axioms we used in the process, and there are really two kinds. I wonder whether you can see the difference between two kinds of axioms. I may throw in a few more into the lower group. So the first kind defines instruction semantics. It is really nothing more than an interpreter for the language that we want to interpret, in which we want to synthesize. Right? You cannot really do less than that. You do need to define that semantics so that those programs are understood. So this is structural operational semantics, more or less expressed in a particular way. The other ones are various algebraic properties on this domain, which you do not need to execute the programs, but you need them to rewrite the program from the specification to the synthesized program. Right? So that we have things like associativity of commutativity of add, associativity, the neutral operator, and here is modeling of memory, the usual way. So there are sort of the minimal axioms you need that give you the semantics, and there is all the other stuff, the domain knowledge. I'll come back to it soon. So what are the properties of deductive synthesizers? They are great. They're efficient because they only generate or explore programs that are correct, because they apply semantics preserving rules. And because of that, they're also efficient, because they only look at programs that are correct. So it's a relatively small space. It's maybe exponentially large, but we'll see it's relatively small compared to what we want to do. And indeed, Denali is scalable compared to prior super optimizers, which what they are called, which were generate and test. Denali can generate instructions of length maybe 30, whereas the previous ones would only scale to length 3 or 4. And indeed, such synthesizers have been built for domains that are axiomatizable. So linear filters, linear algebra, statistical calculations, and data structures phrased as a relational algebra on which we know how to do query optimization. So wherever a theory exists, these optimizers are probably the right way to go. Now, what is the downside? The downside is that the completeness, by what I mean not being able to prove it fully correct, but actually completeness in the synthesis sense, that the ability to generate any program that you like, that hinges, of course, on having sufficient axioms. So if you push a button, you don't really know whether the program that you want is going to be derived by applying a sequence of various derivations. Okay? And then there are some domains that are really hard to axiomatize, such as sparse matrices. Specification must be complete, or functionally complete, must fully define the behavior, plus it must be something from which you can start the derivation. It must be an input. It must be in the form that the derivation can accept and then transform into the resulting program. It cannot be something partial. It cannot be an input-output pair that describes the desired function partially. So that limits what specification you can use, which is somewhat limiting, or maybe more than somewhat. We'll cover that. And then finally, it is difficult to control the shape of the resulting program. Often you don't want just any program that computes the function, but perhaps you want to write half of it because you know how to write it and you insist that it has a particular form. and you want the synthesizer to do the rest. If you let the derivation completely to a synthesizer, you usually don't have such control. So the solver-based synthesis, called inductive one, for a reason I'll explain, achieves these, of course, by trading off something else. So what are some of the challenges ahead of us? Well, we would like a complete synthesizer, again, in the synthesis sense, that it can generate any program we want. And we would like to do it while teaching the synthesizer as little as possible, a small number of rules. And ideally just that operational semantics of the language and nothing more. No additional algebras if we can get away from those. Efficiency, well, what we are solving is a second order formula. The object we are looking for is a program which is not a value but a function. Yet the solvers that we want to use are probably first order solvers because they are generally more efficient. So the question is, how do we encode the second order problem into these first order solvers? So these are perhaps the two most interesting problems that we cover technically. So in the first part, we look at three things, which is what are partial programs, what is inductive synthesis, and we'll write the minimalistic synthesizer in the sense that we will not have a tool that produces the necessary formulas. We'll do them by hand, but that should explain how we do things. So the first thing you need to do is take your language in which you want to synthesize, and that could be pretty much anything, and prepare it for synthesis by adding two constructs. And these could essentially look like this. So first you write a specification, which by the way doesn't need any special constructs usually, although more constructs could help. And the purpose here is just define input-output behavior. So this function here just computes x plus x. Then you write what we call a sketch. More generally, it's a partial program, a program that has some templates in it, some holes, you could say. Okay, and what do these holes say? These are placeholders that are substituted in this particular setting with an integer constant, such that the specification is met. It's the synthesizer who does the substitution. And what is the specification? Well, it's given by the implements keyword in this case, and what it says that the specification and the sketch, after the sketch is completed, must compute the same value, must agree on all inputs. And so the result in this case, of course, is a program where the hole is replaced with constant 1, because if you shift x to the left by 1 bit, you obtain the value x plus x. So it's not a particularly difficult synthesis problem. But this is what it takes to get your language ready for synthesis. Of course, you realize that instead of the keyword implements, which is not necessary, you just need assertions that state some safety properties about the program. So those can be used equally to state the correctness condition. So what is synthesis the way we phrased it? Well, that partial program, we'll just call it sketch because the word is shorter, defines a candidate space. Right? Essentially, for every completion to the sketch, we have a new candidate program. Most of them are, of course, incorrect with respect to the spec, but we'll search the space for one program that meets that specification. Usually we cannot do it exhaustively. Those spaces are bigger than 10 to the 10, often 10 to the 50 or so, so we need to do better than enumeration. And we describe that space symbolically with a formula in such a way that the solution to the formula gives values for those holes. And once you plug in those holes into the original sketch, you obtain the desired program. So the solution to the formula indirectly identifies the program that we want. What constraints these are, of course, is not obvious from the slide, but we'll talk about it shortly. So visually what happens, we'll take a spec and a sketch, run them through a translator to a logical formula that goes into a solver. You can call it a synthesis engine, which produces values of holes, right? So the question marks are lifted to some symbolic variables. One is a suitable value for our example, and then just the code generator substitutes that value into that sketch, and you get the desired program. Okay, so one example that we'll use here to motivate a lot is an example that comes from a sketch contest that we did with with graduate students in a class, and one student picked a problem that he previously had to solve a summer ago in the context of some simulator that he was building. And he had to do 4x4 matrix transpose for some reason. He His implementation was slow, but then he discovered there is an Intel SIMD parallel instruction that could accelerate it. So here is how he went about solving it. What you see here is a specification. It's a function that accepts a 4x4 matrix, flattened here, linearized, and produces another 4x4 matrix. And it iterates over I and j, and it does the usual transpose bit from ij to ji. Why these matrices are flattened? Because this way gives him more freedom to apply the instruction. Essentially, the parallelism has more freedom in how to manipulate the data than when it is expressed as true two-dimensional matrix. Here is the instruction. The instruction accepts two words, x1, x2, well, not two words, two vectors, 4-element vectors, here they are. Outputs another such vector here, and what it does, for each of these elements, it picks one of these four. So either this or this or this or that. Same here, except these are taken from those, and this one is also taken from those. And of course, 2 bits control which word is selected here, another 2 bits control which are selected here, and so on. So it's technically a semi-permutation controlled by 8 bits. And here is the insight that he had. The insight was that in order to transpose the matrix, he cannot do it in just one phase of shuffles with this instruction. He realized, I don't know exactly how he got that insight, that he needs to create an intermediate matrix, perform some shuffle from the original one, and then the intermediate one will be shuffled into the resulting matrix, which will be the transpose. And you see, the insight, we do not automate insight, but we let programmers to state it with some partial program, and we help complete it. Or in fact, prove it wrong. If there is no completion to the sketch, we can prove definitely that there is none. Okay? So how is that insight expressed in this partial program? Well, so here we have a definition of a sketch, takes a matrix, outputs a matrix, implements the specification you just saw, which was sequential. We create the target matrix, the intermediate matrix. Okay? And now this is the first phase. We perform some number of such instructions. We pick 4 words from M, starting at some position. Which one? We don't know. The synthesizer will know. And we pick another 4. And how we shuffle them, again, is up to the synthesizer to figure out. And also where we write them into intermediate matrix is left unspecified. And there will be a sequence of these instructions. That's phase 1. And phase 2 goes from S to T, and then we output T. Of course, he doesn't have to write it by cut and paste. Instead, there is a construct we call a repeat or loop, which lets the synthesizer decide how many of these instructions are going to be used in each phase. And the synthesizer does it in such a way that even though we make a copy of this statement, the copy will have each a fresh hole, so each copy can have a different solutions to these holes. And here is the solution. And here are the various values we synthesized. Here are the bit masks. Okay? And yes, this is something that you don't really want even your grad students to compute, ideally. So what he said is that he spent about half a day previous summer figuring it out, and our synthesizer will solve it now in less than 5 minutes. So I'll go and show you the demo for it. So if you go to the online version of the sketch, which was a synthesizer built by Armando Solar Lezama when he was here at Berkeley and then generalized greatly after that. What you see, I don't want to run it for 5 minutes, but I have made one change to the sketch. I wonder if people can observe what the change was and why that should make it faster. Yes, I have added the additional constraint that these 2 loops, we don't know how many steps they take, but they perform the same number of steps, right? So that is an extra constraint that helps the synthesizer solve it faster. And it is synthesizing and should be done on the order of 5 seconds. And so here is the specification reprinted. Here is the result with the values synthesized. And this took about 5 seconds, 5.7 seconds. Okay? Now I want to get to the question of how did the designer know that there needs to be two phases, and I actually don't know. But what I want to show you is how he could have come up with the insight. I can, I can go here to this partial program, if I can make it visible. And I can remove the second phase. So now we are describing a space of programs that only perform one shuffle phase. And I will run the synthesizer. And it will tell me relatively fast that the spec and the sketch cannot be equal. So in other words, the hypothesis that there exists a one-phase shuffle program has been proven to be wrong. What was that? Oh, I see. Oh, that is true. So maybe it will actually run slower. Okay, I need to lower the font. Okay. Okay, so here is the result. All right. So what we have done, we have made the sketch a little bit simpler by extra insight, and what it indicates is essentially the trade-off between how much information you put in, how much insight, and the scalability. So if the problem is too hard, you can think a little bit harder and put more constraints in and synthesize the rest. So this accelerated it from a few minutes to 5 seconds. And the other one was that you can actually test hypotheses and see whether programs exist. So now I want to talk about how we actually solve the synthesis, but this may be a good place to make a brief stop and let you ask questions. So you're asking about Denali, presumably, right, which synthesizes a whole set of equivalent programs. Well, at that point, it does what you could call auto-tuning. It walks over these instructions and discovers which of them is faster. In their particular case, they actually schedule these instructions on a scheduler implemented as a set solver. So they were scheduling constraints to figure out how fast they would run. But you could equally run them on a real machine and pick a fast one. So I didn't go into that because I think the process of creating an equivalent program is the more interesting one here. But it does essentially, at that point, some exhaustive search to look for a fast one.
I had a quick question.
Okay.
It seems like an alternative to talking about writing a program versus writing a spec is talking about how abstract the spec
Yeah, we'll get to the specs and to what extent they can be abstract, right? To what extent they define the actual input-output behavior. And in a sense, we'll give you a lot of flexibility in how you write the specification. Looking forward, essentially you can conjunct multiple constraints on the behavior, on the structure of the program. These together are all considered in synthesizing the program. So if you want something abstract that says, well, the result needs to be positive, if you have other constraints to throw in, it might narrow down the space enough.
So I had a question. So in program verification, when you're looking for inductive invariance, it can also be posed as the second order question, right? Does there exist invariance?
Right.
It didn't seem that different from the verification problem.
Well, you could say if we are looking for inductive invariance, these invariants are, after all, just expressions, so they are programs. So in a sense, the problem is the same.
What is the search strategy being used?
The question is, what is the search strategy being used? So we'll get to it. There isn't one. We'll talk about two, I think. Yes.
Yes. From going to the sense about what is your constraint domains? That is, we have seen multiple domains and for number of steps or parameters. But what is the constraint domain?
What is the domain of programs or domain of inputs?
Of the constraints with provide the values for holes.
I see. I think what is the domain of holes? Well, a short answer is that we start with integer holes, but it is interesting, of course, to have holes that are in other data types. Booleans, of course, that's as easy, but holes that could be lists, list values. And Emina will cover that to some extent. I'll show you shortly that, of course, you can express everything over holes that are just Booleans or integers, right? And so that's a good question. Keep the thought. We'll cover that shortly. Okay, so imagine that we do have a program expressed as a logical formula. What do we do with it? So I'll cover how to obtain that formula soon, but here is a program that returns x plus x, and here is a formula which essentially relationally states that the output y equals x plus x. Okay? And how you obtain the formula and what it expresses is essentially no different than in program verification with concrete semantics that is symbolic, such as Java Pathfinder and CMVC. There is nothing new really here. The first thing I want to observe is that if you have an interpreter, sort of relational interpreter, solver, you can use it as an interpreter for that program. Right? So if you have your formula that describes the program and you assert x, which is an input, you solve for y, you effectively run the program on the solver and obtain the output value. You can also assert the output value, solve for the input, and essentially invert the program. So by just having a symbolic description of the program, you can interpret it, you can invert it. And it is this bidirectionality, so to speak, of solvers which enables synthesis. How does it enable synthesis? Well, imagine that we take a sketch, which is a program with input x, output y, and it has these holes inside, okay, which parameterize it. And you create a formula now with 3 arguments. Okay? And here it is. Right? So this is encoding the bit shift operator. Y again is the output. So what we do, if we assert formula plus input plus output, and we solve for the whole, then we obtain a completion of the program. Of course, what we get, we only get a program that is guaranteed to be correct on this particular input, on x equals 2, but if those inputs are chosen carefully, we get the correct program, correct for the rest of the inputs as well. Of course, you need to choose those inputs carefully, because if the first one, in this case, is 0, corresponding output is y equals 0. How did we get it? Well, we just evaluate the specification on that and obtain y. This input, x equals 0, doesn't give us enough constraints, so you need to get additional input-output constraints to constrain h to such a value that it gives you a program correct on remaining inputs. How we find those inputs we'll cover in part 2 of the tutorial. Let's assume that we have a set that is sufficiently constraining. Okay, so what we have done is called inductive synthesis for the reason that we ask a solver for a program that is correct on a few inputs, and then we either pray or test or verify that the program is correct on the rest of the inputs as well. It's best when you can verify it. Sometimes testing is all you can hope for. We'll describe how to find those inputs. But a note before we go on that I want to make is that we do everything on concrete inputs. So the inputs on which we want the program to be correct, the one produced by the inductive synthesis, are concrete. And this is useful because we take this 2QBF problem, which means we have 2 alternating quantifiers, and we turn it into a set problem by eliminating this for all quantification, because instead of for all x, just insist that the program is correct on that small number of concrete inputs. Okay, so now we'll talk about how to translate a program to a formula, and Emina will cover that part.
Okay, so essentially we're going to do it in 4 steps. The first thing that we're going to do is we're going to get rid of all the funny synthesis constructs. We're going to convert this program into some valid program in the host language. Then we're going to unroll the program into a bounded acyclic program. So we're going to get rid of all the loops, right? So as Ra said, we're only correct up to a certain bound on the size of the program. So this unrolling is the first step that we're going to take towards bounding our search space. The third thing that we're going to do is we're going to make the program functional. So we're going to get rid of all the ugly features such as mutations, state updates, and so on. And finally, when you end up with this really simplified functional programs, you can essentially just read off the formula and convert it into the language of your favorite constraint solver. Now you can use whatever constraint solver you want. You can essentially translate this to a Boolean circuit, but if you're familiar with how SAT encodings work, this is actually tricky to do, right? So it's actually pretty hard to come up with an efficient CNF encoding, and it's kind of hard to generate these millions of variables and clauses by hands. So you're probably better off using something that sits above a SAT solver, for example, a model finder or an SMT solver. The particular solver that we're using is well suited for reasoning over these bounded domains, and it has some nice features that are not available to other SMT solvers because they have to do complete reasoning. For example, you can express transitive closure in this particular logic that we're going to show you how to use, and that's convenient for talking about heap shapes, saying that a list is acyclic, for example. So in part one of this tutorial, I'm going to show you how to translate this expose example manually into the logic of this solver called Code, and the logic is based on relations, so you can think of it as database relations. And in the next part, we're going to show you how to automate this process. So whenever you have a new problem, you don't actually want to encode it by hand. You want to have some kind of a compiler, which is going to compile your program instead of to, bytecode instructions, for example, to formulas, and then you can invoke solver on it and perform synthesis. So here is the program that you've seen before. This should look pretty familiar. We've simplified it even more. We've actually unrolled that repeat statement 4 times in each case. And we've also taken away the part where we're guessing where the shuffled bits are going to go into the intermediate matrices, right? So we're just fixing them here. This is going to work, of course, if there was no solution. In this case, the solver would just tell us. Okay, let's apply our steps. The first thing that we're going to do is the easy thing. We're going to get rid of this implement statement. And how are we going to do that? Well, we're just going to turn it into an explicit assertion, right? So what is this saying? The correctness condition here is that this transpose matrix T that we're computing using this shuffle instruction is actually equal, element-wise equal to the transpose matrix that you would get by applying that simplified transpose spec procedure that Ras showed you before. So the next thing that we're going to do is we're going to get rid of these question marks. And we do that by essentially introducing fresh symbolic variables. So each hole corresponds to a fresh variable. We're just going to give them some names. I gave them names that are meaningful here, so you can read the slides, but they're not important. You just know that they're unique names, and that these actually stand for symbolic integer variables. The next thing that we're going to do is we're going to make these array accesses, these kind of MATLAB style reads into the array explicit. We're going to replace it with an explicit read function like this. Okay? So what's happening here is we're saying that instead of that array access, we're now calling this read4 function on a matrix and a starting position, and it returns a new 4-element array which contains the elements AI through A plus 3 in the obvious way. Okay, so that's all the read function does, just returns a new array. So we're almost done. The last step is to really turn this into a functional program. So it's still not functional, right? Because we have these array updates. So we're going to do that by turning these write instructions into explicit update functions, calls to an explicit update function that returns new copies of the array where some elements are updated. So this is what it looks like. Okay, so we're introducing new variables. So now we have this S0 is equal to a copy of S in which elements starting at position I are replaced by this delta array, the 4 elements from the delta array. Okay, so far so good. I hope everybody should believe me at this point that it's the same program, right? And we have no mutations in this case. So this is pretty much it. So if you're familiar with some SMT solvers, for example, Z3, you could essentially just read off logical formula from here. So let's see how we do it in this particular logic called relational logic that we're going to use today. The first thing to note is that in this logic, everything is a relation. So we don't make a distinction between sets and scalars and so on and so forth. A relation is a mathematical relation. It is a set of tuples where they all have the same length, and tuple is a sequence of elements, uninterpreted elements, that are drawn from some finite universe. So in our case, the universe of interpretation from which we're going to draw solutions to our holes is going to be the simple universe with elements 0 through 15. Now, I'm calling them 0 through 15, but as it is, they don't actually have any meaning, right? The solver doesn't care. I just wrote those numbers, so you know what I'm talking about. So you have some examples of tuples there. So the sequence 0, it's a unary tuple. And you have some examples of relations. So the first relation contains the tuple, which contains the element 0. So it's a singleton unary relation. This is what we're going to use to model a scalar value. The second relation that you're seeing is a unary relation, which we're going to use to model a set, or you can think of it as a type, right? So if you want to model the set of all lists in a program, you would model it using one of these things. So it's a unary relation. And at the bottom, you have a binary relation, and this is what we're going to use to model integers. And it is also what you would use to model the heap in an object-oriented program, if that is what we had. Okay, so let's see how to translate this array initialization statement. So first of all, note that we're modeling an array as a binary relation from integers to elements. In this case, the elements of the array are also integers. And this initialization function, what is it doing? I mean, it's just basically setting everything to 0, and that is exactly what the relation up there is showing. So we're just binding it to some name S, so that later, as we're translating the program, we can refer to it, right? So we're just introducing some syntax called S, and it is bound to this relational value. Now, how are we going to translate this reference to the symbolic variable mx10, which refers to one of our holes? Well, it's going to be a unary relation, but before we hand this off to a solver, we're going to conjunct it with these two additional constraints, which ensure that this relation is a scalar. So what are we saying here? We're saying that this variable can take a single value from the set 0 through 12. Why 0 to 12? Well, recall that we're using this variable to index into an array of size 16, and from that index forward, we're going to read of 4 elements, right? So clearly, the maximum value that we can have there is 12, so 0 to 12. How about this read function? How are we going to translate this functional read? Well, this is the semantics that we want. Here's a sample array that you see at the bottom. Let's call it A. And it's mapping 0 to 1, 0 to A, 1 to B, and so on and so forth. So it's basically an array consisting of A, B, C, D, E. We want to read off 4 elements from this array starting at 1. So the result, in the way that we're modeling these arrays, should be the binary relation that we have at the bottom, right? So now 0 should be mapped to B, 1 to C, 2 to D, and 3 to E. And how do we achieve that using relational operators? Well, it's also shown in the slides, and I'm going to just go briefly through the syntax so that you know what it's actually saying. So this funny dot operator here is called relational join. If you're familiar with the database relational join, it is just like that, except that we drop the matching tuple. If this doesn't mean anything to you, you should think of this dot operator as essentially doing a get on a map. right? So your binary relation that we have here is an array, hence it's a function. The thing that we have on the left-hand side is a scalar. So when we do this join, we're just looking up this key in this map. And that is the output. There's a definition on the bottom. The other operator that might look slightly strange, and it's slightly different than what you would have in set theory, is this cross-product operator. And the only difference is that we actually concatenate the tuples as opposed to creating a tuple of tuples, right? So it's not higher order, we just concatenate the tuples. And that essentially fully encodes the semantics of this read statement. I hope everybody sees that. If you don't see it, you should ask me questions.
What does read for read into?
What does it read into? It reads into an array that starts at 0, right? So here is desired semantics, right? So it means that when we're doing this cross product, we're saying, okay, create me a relation using this union operator. The first tuple is going to be 0 times, or actually concatenated with whatever we read at position I, plus 1 concatenated whatever we read at position I plus 1, and so on and so forth. Is that clear?
What if I greater than 1? What if the value of I is 2?
It doesn't matter. So I itself is also encoded relationally. It's basically one of these set of tuple things, right? So this, I didn't actually show you how this add 1, 3 or add 1, 2 operator is implemented. But what it's saying is, if I is 2, when we do a join, it's going to look up the value of this function at position 2, right? And then this add I plus 1 operator is going to return a relation that contains the value 3. Then we're going to read the value 3 off of it and continue.
But it's going to be out of bounds.
Out of bounds.
Oh, out of bounds, right? So I haven't actually shown you how to handle that, but in this case, you don't have to worry about it, because the only things that we're using to access the arrays in our encoding are these mx variables. And note that I've constrained the maximum value in the mx variable to be 12, right? So the solver is never going to pick anything greater than 12, and we know that the array that we're indexing into has at least 16 elements. So we don't have to put any array bound checks. In general, you would actually have to, but I'm encoding, because I'm doing a manual translation, I'm encoding more knowledge into this than you could if you were compiling this automatically. So in fact, you're right. When we're doing an automated compiler, we do insert bound checks using assertions, right? In this case, I've explicitly set the upper bound on this indexing variable to be 12, so we don't have to worry about out of bounds checks.
So I'm a bit lost. So is the previous thing you had was already encodable in an SMT solver, right?
Yeah.
Theory of arrays.
Mm-hmm.
Theory of relations, is this particular synthesis that has some certain benefits, or why are we moving to a theory of relations?
It doesn't matter. You can actually encode it using an SMT solver, but it turns out that this particular solver that we're using is extremely efficient for reasoning about finite domains. And everything that we're doing here is finite. And this one is highly optimized for that. It has things like symmetry breaking, which is pretty important if you're reasoning within some finite universe and it's fairly large. So SMT solvers are optimized when you have to do kind of complete reasoning, for example, over integer arithmetic or arrays or something like that.
Can you say why relational is easier to do than, or
Then,
is it just a tool that exists, or is there any reason why a relational logic would be more amenable for finite tree analysis than, let's say, theory of arrays?
If you had a solver that could translate theory of arrays, you could use it as well. But the thing that's very nice about this particular logic is the inclusion of transitive closure, right? So you can write very easily things like, you can say a list is acyclic, right? Because you can simply say, if I'm modeling this list as a binary relation called next, and I take a transitive closure of this relation, and I intersect it with the identity relation, the resulting set is empty, right? So I can basically say that things that are acyclic. That would be much uglier to say if you don't have transitive closures. You would actually have to, spell it out explicitly and probably make your SNT solver run a bit slower than it normally would. So it natively handles these things.
Even for bounded model checking, this would be a good idea.
Yes. So it's actually the solver that we're using has been used for bounded model checking for Java code and just like imperative programming languages. But you can think of it, the way to think about this as essentially it's just a SAT solver, except that you get a much nicer logic to write in. It blasts out the SAT, but you don't have to worry about the intricacies of how am I going to break symmetries in this space, how am I going to do the CNF encoding efficiently, and so on and so forth. Okay? Okay. One last thing to do, how are we going to translate this right? And this is also pretty easy. Here's the semantics that we want. We have this array A. We have the position at which we want to write for elements. Here's the delta that we want to apply to it, this D relation, and here's the output, right? So we just basically copy everything that is not affected by the write, and from A, and everything that is affected by the write, we copy it from D. And we do that using this relational override operator. And you can think about it as doing a put into a map, right? So it just basically changes the bindings from the keys to the new value that we specified for those keys. That is the semantics of the operator. And I'm going to show you now how this actually looks like in the solver itself. In particular, I would like to convince you that this is not hard to do, A, and B, I'm not cheating. What I just showed you, this encoding, is exactly what I gave to the solver.
Should be good.
Instead of using the syntax that I showed you, I just basically encoded this in Java using API calls to the solver. And to convince you that it's the same thing that I just showed you in the slides, so here are some relations that I created for the holes. They should look familiar. We have MX1, MX2, and so on and so forth. I'm making unitary variables out of those. And here are the invariants that I said that we have to add. So we have to say that all of these relations that we're going to use as indices are singleton relations. So this is the API call for that. And here is what the transpose spec looks like. So this is the spec that Ras showed you at the beginning. It's basically saying that T of 4i plus 1 plus j, whatever. So that's the spec. And here is the shuffle implementation. And it looks exactly what I showed on the slide, right? So we have this call to read for, which is translated as I showed before here, using these joins and products like this. Here's the write operation using the relational override like that. And I'm setting, as I said before, all of these selector variables to have, to be anywhere from 0 to 12, right? So I'm not letting them go over that in order not to have to insert these bound checks. And what I'm going to do here is just call the solver. I have some sample matrices that I punched in here. I'm going to call the solver on this matrix C, which I'm going to convert to relational expression in the way that I showed before. It's just going to be binary relation from integers to integers. So when I run it, the solver is going to think for a little bit. And here's the output, right? So it found the solution. Solving time is pretty fast. This is the translation time, going from relational logic to Boolean formulas. And here are the values for our selector variables that the solver found. And you can see that when we evaluate transpose and transpose shuffle against these particular values that we just synthesized, all of them produce the correct output. And now we're going to go to the second part, and I'm going to hand over back to us.
So details like why 12 could that have been also expressed as a constraint? You put in 12 as an actual number of sites. Do you have expressed that to a constraint?
Yes, yes. This is just simplified for the demo, but you can express all of these constraints, absolutely.
Question. So, just to follow up Madhu's suggestion, I mean, it seems there is the efficiency issue, but there is also the notational issue of writing these in a relational notation.
Yes.
So, is that, do you think that's an overhead that's justified? If you write it in SLP format, like with arrays and indexes and integers, it might be less, might be more succinct in overhead.
So we're actually translating automatically, so it really doesn't make that much of a difference. Yeah, I mean, I just showed it, using these API calls for the demo, but we generate the format automatically. It doesn't really make a difference.
So it might be a little bit more verbose than writing it in sort of an SMT tree, but if you look at how sort of SMT expressions are constructed programmatically in, say, a Java API, you wouldn't see that much difference, so a lot of it because of that.
Actually, what I was going to suggest is not even SMT, but use an intermediate programming language like Bodik or Y, where you can actually import those programs almost very naturally.
Right.
So might be on the
So code has been used as the solver for Alloy, so you could in principle use Alloy to get a more sort of concise encoding similar to the pseudocode you saw on the slides. But I want to get back to the point that Madhu asked, which is why not use a theory of arrays, essentially symbolically model the memory. And we did such experiments before, essentially compare theory of array encoding with the one where you blast the array and you create a separate variable for each element of the array, and you model it at each step of the execution. And the theory of array did really poorly. Probably 2 orders of magnitude or 3 orders of magnitude slower than blasting it that way. So indeed, for the finite domains, and in particular for the inductive synthesis, which does search huge spaces, usually bigger than verification does, it does make sense to do it in a finite setting. I want to summarize the first part. So what do we know? That partial programs define the space of candidates. Most of them are wrong, so we need to find one. And we pose the search as symbolically by lifting holes into essentially arguments of the program, translating the functional program into formula, finding concrete inputs that make it more efficient, also known as observation in the inductive synthesis setting. And then you find the holes that indirectly find the program. We used concrete semantics for 2 reasons: that making it concrete gives you the necessary efficiency, and second, that concrete semantics is easier obtained than suitable abstract semantics. So before we go to part 2, I want to stop here and maybe give people a 5-minute break. Okay, so we'll start with the second half. We have about 30 minutes to go, and we'll talk certain important questions in depth. The first one is, well, the language we showed you with integer holes is clearly not quite satisfying, right? So we'll see how to make it more general and also how to write specs. Then how to write a do-it-yourself synthesizer if you do not want to use our Sketch, a big tool which has many optimizations, but is sort of a general purpose language. You need to do synthesis in a particular setting, say in your own data flow language, how you would do that. And then how to turn solvers, satisfiability solvers, into synthesis engines, which are 2QBF solvers. So we'll talk about the language and programming, then about the translation to formulas, and about solvers. Okay? So one motivation for doing this sort of style of synthesis with constraints in concrete semantics was that you have a lot of freedom now to use whatever specs you find natural. Why is that interesting? Because when writing specification in synthesis, or maybe in general, you often run into problems like this. You say, I find it really hard to write a full behavioral spec. There are just too many corner cases. perhaps writing the spec is as hard as writing an optimal, fast program. So how do we deal with that? Another one might be, you find it really hard to write a relational spec because getting the quantifiers right might be a pain. Okay? And also, declarative specs may not be so easy to test by running, so you cannot debug them as easily. And perhaps another one is my synthesizer runs forever, so the scalability is a problem. And all of these can be addressed by using the right specification. So what are the specifications we can use? Why do we say they are multimodal? Well, the one that we already have seen is executable, essentially functional. It's a function from input to output, okay? A reference implementation. So for a merge sort, a reference implementation could be a bubble sort or insertion sort. The other one is what you could call declarative or a checker. It's a predicate that accepts input and output and answers whether output is a correct value for the input. So sorting might be easy to state that way. You say the output is sorted and a permutation of the input, okay? But sometimes stating the permutation might be difficult in what you are writing, so you may want to write a partial declarative specification, just assert sortedness. Then various safety assertions, as we alluded to, both sort of concrete. You may want to say anywhere in the program that x is 0, and abstract in the sense that you will say p must be of some type foo. And referring to types is already a notion of using abstract specifications. The best specifications are those that you get for free, and those are implicit language assertions such as bounce checks and null pointers. Essentially, the semantics of the language insists that the program, in order to terminate, cannot run into any exceptions, such as null pointer exception. And so these generate as well constraints that are useful for the synthesis process. And finally, there are input-output pairs, which of course should not be underestimated because these might be very easy to write. The key point is that all of these can be translated into the constraints and conjuncted into the specification that you feed into the synthesizer. So there are two classes of constraints really, and this is very useful to keep in mind. One of them are behavioral, those that define what the program should do in the input-output setting, right? It's what, this is the what of the thing. And these could be full, such as executable specs which compute the output. They could be also partial. For example, input-output pairs are necessarily partial. They don't tell you what happens on every input. Safety property would be partial. Or declarative spec, which tells you for sorting that the output is to be sorted, but doesn't say it needs to be a permutation of the input, is also partial. Okay? Now, structural properties describe what the computation does internally. So this is how the computation proceeds. And these are typically expressed in a sketch because it's a skeleton of the program. But these can be further constrained by technically safety assertions, such as you count the number of iterations that the program needs, and you insist that it is, say, less than 3 times the log of the input size. So this is a poor man's way of asserting that you have logarithmic behavior. Okay? So you can insist on that. You could implement a little sort of cache simulator in your semantics, essentially model a little cache, count the number of cache misses, and again assert that the program that you synthesize has smaller number of cache misses than some desired bound. So all of these, even though they are assertions, they really constrain how the how the computation proceeds. So what are the lessons now that we know what the specifications could be, what format they have, and what they constrain? Well, if you find it really hard to write full behavioral spec, it's good to keep in mind that the sketch, of course, defines the structural properties of the program, but it also limits the set of functions that space can compute. So for example, for sorting, if you know that every program defined by your sketch performs a permutation of the input, then your behavioral spec does not need to say that the output needs to be a permutation because you have constrained it perhaps indirectly in the program, in the partial program, in the sketch. If you find it really hard to write the declarative spec, perhaps you don't need to write first-order specification, can use reference implementation or input-output pairs. And finally, when the synthesizer runs forever, it's good to realize that you can break down a large synthesis problem by asserting some properties about intermediate values. So if you know that on some input the program needs to have value 5 here and value 7 here, or the list needs to have a particular structure, you can assert those, and that effectively decomposes a big formula corresponding to the whole problem into smaller ones by getting intermediate values and helps scalability tremendously. So much about specification. That's an important topic that seems sort of dull but it is key, writing the right specs. So I'd like to stop here and let people ask questions. Okay, so why just integer holes? Well, sometimes you want to complete your program with arbitrary expression, not just integers. For example, you want to synthesize an array index expression. Well, that can be done easily by just saying that you need some affine expression over I and j, and you just need 3 holes for that. You can describe polynomials this way, right? And what is interesting is that you can write so-called, we call it generators, that can do it in a reusable fashion. You can keep them in the library. So imagine we want complete a sketch with one of these expressions, okay? And you can write it like that. So if you see what we are doing here, this is just an ordinary function, a recursive one, okay? Except it is special in the sense that when you call it recursively, you get an inline, and therefore every recursive invocation gets a fresh copy of this hole. And now the synthesizer has a choice at each level to pick the right value of the hole, and it returns A or B or some expression plus some other expression or minus. Now, if you look at it the right way, what you will see that this is nothing but a context-free grammar, and what the holes control, they control a derivation from that grammar. So you see how integer holes actually now act as Gödel numbers for identifying programs from that syntactic space defined by the sketch. How is it useful? Well, here is a little cute example where the specification is a polynomial. Okay, here is a sketch which needs to be equal to the specification. It has 2 terms that it multiplies here, and here it has a hole that will be completed by a polynomial of up to degree 3 over x. Okay? And here is the definition of the polynomial essentially as before. You either return a constant or x times polynomial of a degree 1 less plus a suitable constant. So again, it's a grammar defining a polynomial. As you can guess what it does, this performs a division of this polynomial with that polynomial, and here is the result of the division. 2 points to make. We didn't have to teach the synthesizer anything about polynomials or polynomial division. Again, it only knows operational semantics. It knows what is an integer variable. It knows what is times, what is plus. That's all it knows. Of course, it's not an efficient way of dividing polynomials, but you didn't need to teach it any special knowledge. Another point is to make that you can extend a language like Sketch with holes, with metaprogramming by essentially writing little grammars like that, and you don't need any special support for metaprogramming such as meta variables. Okay, this is a, yes?
So if you have poly of y comma x, where y was an integer, what would happen?
If you're asking what would happen if this is y, well, maybe any more interesting question is what would happen if this was actually a hole, right? So again, the synthesizer would feel free to find a polynomial of a suitable size. Of course, under the covers, the value of the hole sort of grows incrementally, but...
So the unrolling of the recursion will make sure it's bounded.
Exactly. It's sort of a semi-algorithm that grows that space until it suffocates under its own weight, of course, or gives you a solution. This is a question that came up. Can we only synthesize programs like transpose, which has a fixed size, 4x4? And of course, the answer is no. The way you do it, imagine that you want to synthesize a program that handles input of an unbounded size, sorting for any arrays, multiplications of large integers for any size, or just linked list operations. So the way you do it is that you synthesize the program on a sample of inputs, again, of various small sizes, but you do it in such a way that you understand that the sketch has a sort of symbolic variable n, which is the size of the input. In the case of the list, there is no n, but the sketch will sort of have a loop or recursion that walks over the list. And so while you synthesize a program that works on the few sample inputs, when you generate it out, it will still contain the loop, and therefore it will accept and hopefully work correctly on all other inputs as well. And so it's based on the small world hypothesis, which for verification says that if the program is correct on all inputs on up to size k, it's correct on larger inputs as well. That adapted for synthesis essentially says that if you synthesize a program correct on the small world, on all inputs from the small world, it might be correct with the larger inputs. Of course, there are no guarantees. This is only as good as bounded model checking. The point is, though, that it can be done. So now Emina will tell you about building a do-it-yourself synthesizer quickly. Essentially, she'll tell you about how to convert a program into a formula.
Or rather, I'll tell you how to do it mechanically, not by hand. So what does it mean to build your own synthesizer? Well, basically, we have two requirements. First of all, it depends on what the domain of a program is that you're trying to synthesize, okay? Maybe you want a general purpose language like Sketch that's going to have some holes, it's going to have loops, ADTs, perhaps mutation, perhaps Boolean integer holes, and so on and so forth, but maybe not. I mean, it really depends on what you're trying to do. Maybe your synthesis language is very, very simple. But what we really want to have is we want to have some kind of a support to grow the language to support different kinds of holes, like list valued holes. What we've been showing you so far is how to encode things in integers. And as Raj said, when you have integers, you can encode everything. But often, if you have native support for certain kinds of values, like list values or sets and so on and so forth, you can actually do better. You can make your synthesizer scale better. So, okay, so you may want a general purpose language, and of course, you want to be able to synthesize the values for these holes automatically, right? You don't want to write a manual translation every single time you have a new problem. So how are we going to do that? Well, we're going to build a compiler that essentially does partial evaluation of programs, and it translates them to formulas rather than to some kind of machine instructions that you could perhaps execute. We're going to show you how to build an inductive synthesizer in the sense that we are going to assume that sufficient inputs are given. Ras is going to show you later on how to pick the inputs intelligently in order to make sure that what you synthesize is correct for the bounded scope that you've decided on. And of course, we would like to build a synthesizer very fast. It shouldn't take your entire PhD to do it. That's basically it. How are we going to do it? Well, let's first see what problem we need to solve. We want to take in a program which itself takes in two kinds of inputs. One of them are regular inputs, and the other inputs are holes. And given these inputs, it produces something. So the synthesis problem here is to solve this formula. We want to find a set of holes such that the program satisfies its spec on the set of input-output pairs that were given to it. So this is the inductive synthesis. We assume that input-output pairs are given. And how are we going to do it? Well, we're going to build this partial evaluator. And as you're going to see, it's going to generate a formula that's parametric in the holes. And it hard codes everything else. And the holes in the formula, of course, are free variables. We're going to do it in 3 steps. The first step is you're going to define your language and build a concrete interpreter for it. So you essentially want to be able to write those executable specs, right? So you want to be able to write a program that runs. Then we're going to add holes to the language. In this case, we're just going to add integer holes and see how it works with that. And after that, you want to extend your interpreter to implement this synthesis translation procedure. How is it going to work? Well, when it sees the holes, it's going to interpret that hole as a symbolic value, a fresh symbolic variable, let's say in this case called x. When it sees an operation on a concrete value, it executes it using the concrete semantics, right? So if the interpreter encounters 1 plus 1, it's just going to return 2. It's not going to do anything clever. When it sees an operation on a symbolic value, however, it's going to return a syntax tree, a symbolic syntax tree that encodes the meaning of the symbolic operation. So for example, if it encounters 1 plus question mark, and the value of this question mark is the symbolic variable x, is going to return a tree that says 1 plus x. Okay? So far, so good. So this is the intermediate language or the residue of this program that's going to be generated when the interpreter finishes interpretation. At the end, if it's left with a concrete value, it's just going to return it. at the console, right? Because there's nothing to do. If it has a symbolic value, it's going to call a solver to find a valuation for it, an interpretation for it. So how are we going to implement the step one? Well, I said you should define your own language and build an interpreter, but that's actually too hard. What we actually want to do is steal a language, right? And if you're going to be a thief, you should be a good one. So we want to steal a language that is suitable. And something happened to our slides, Ross. Yeah, but we want to steal a language that is suitable for building the synthesis tool. And there are essentially three requirements, right? So the first one is that the language has to have metaprogramming abilities, right? Why is that? Well, since it already comes with a concrete semantics, if it also has metaprogramming abilities that allows you to extend the syntax, they will also allow you to hijack the concrete interpreter and teach it how to reason about symbolic values. Preferably, it should also have a small core. I mean, you can have a very large language, of course, but it's going to be harder to implement. Here, we're going to be super lazy, and we're going to use this new language called Racket, which is a version of Scheme. And the entire language, you're not supposed to read this, but this is the entire language. It fits on one slide. Small font, but it fits on one slide. This is the core language that we're going to hijack. And how are we going to do it? Well, we're going to add some named holes to it, right? And what does that look like? Well, here's the grammar of the language itself, and we're going to add one additional construct. We're going to allow you to define a variable, a symbolic variable, and tell us whether you want a number or a Boolean. And from the point of view of the user, this is what it looks like. On the left-hand side, you have a Racket program that computes the sign function. And if you're not familiar with Lisp, I'm just going to go through this very briefly. But basically what it's doing is defining a global variable z, and it's assigning the value 0 to it. And it's saying if y is less than z, it returns -1. If z is less than y, it returns 1, otherwise it's 0, right? So it's just a very simple implementation of a sign function. Now, in our language, Rosette, there are two differences. First of all, we tell the Racket environment to load all the extensions that enable symbolic reasoning, and then we're now free to make the z symbolic, right? So it's no longer 0. We don't know what it is. It's a whole, and it's a numerical one. That's what we told the solver. What happens behind the scenes? Well, we're going to make use of those metaprogramming facilities. So whenever the Racket compiler sees defined symbolic, what it actually does, it applies this macro that's defined up there and rewrites this program into another one in plain Racket. So what's happening here, it's using Racket's own mechanism for scoping and variable definition. So what it's doing now, it wrote this, it's saying, okay, just give me a plain Racket variable z, but instead of making it an integer or some concrete value, we're going to make it into this funny leaf of this AST, right? It's going to be a symbolic variable, its name is going to be z, and its type is going to be a number. If this is the only thing that we did, and we tried to run this program in Racket, it would fail, right? Because we have something that says y is less than z, and Racket doesn't know how to compare y to a symbolic value z. So we have to do a little bit more work. We have to teach the interpreter how to interpret less than and how to deal with symbolic values here that appear in the test of that conditional, right? So first, let's go with the less than. So this is what it looks like. This is how you hijack the interpretation of that. It's saying lift the interpretation of the symbol less than to use this funny function that we just defined, right? So whenever the user writes less than in their program, it's actually substituted with a call to this function. What is this function doing? Well, it tests. If both of its inputs are concrete numbers, it just applies the primitive less than function to evaluate it on the spot, right? If one of them is symbolic, it creates this AST, right? It's just a struct. It's a tagged AST where the tag is the operator being applied, and it attaches the two arguments to it. So that's it. That's all it does. The other thing that we have to do is we have to handle the conditionals. So I'm showing you a very simplified version of this that has no side effects. If there are side effects, you have to do a little bit more work and be a bit more clever. But if there are no side effects, it's actually pretty easy. So what does this do? It says that I'm defining a macro. Whenever a user writes if in their program, I am going to substitute that if statement with this let expression. The let expression takes the test condition and sees whether one of three things is true. If it's a concrete true value, then it executes the then branch, otherwise it executes the else branch, and if it's a symbolic value, it constructs a phi node, or an AST representing the phi node. And that's it. I'm going to show you very briefly how this works.
I think given just a few minutes, we'll probably have to leave the demo for... so we have a fewer minutes than we expected, so we leave the demo for the break, and I'll cover quickly the two synthesis engine that we want. So this is the problem that we want to solve, but instead we were solving a problem on just carefully selected inputs without telling you how they are selected. So, well, here is what we've been doing so far. This inductive synthesizer which accepts some input-output pairs and gives you a program that is correct on those. It can also tell you that the problem is unrealizable, say the hypothesis is invalid. You do not have an algorithm, the correct one expressed in the partial program. But if it gives you a candidate, you can send it to your verifier, checker, whatever checker of your choice, or a tester, in fact. And if it approves it on all the remaining inputs that you care about, could be a few more, could be a small universe, could be indeed all inputs, then you are done and your correctness guarantee is met. Or if you fail, then you obtain a counterexample input which is a witness showing that the program is indeed incorrect. And you add that into the set of observations, these carefully selected inputs, until all, so to speak, corner cases of the problem are covered. Okay? So both of these are satisfiability problems that communicate by exchanging counterexamples. Okay, so I wanted to cover the other one. To cover the second solver, what can happen sometimes is that the verification is impossible. You might have a reference implementation, you might have a spec, but perhaps you cannot translate it because source code is unavailable or too complex. So you cannot ask a verifier for a counterexample input. What you can do instead is to ask a solver for disagreeing plausible programs. Plausible programs are those that agree with the constraint so far, but they disagree on some input X. They output a different value. And so you ask the synthesizer for an input on which these programs disagree, so clearly you have an ambiguous system. And now you can ask the specification, which you can hopefully execute, even if you cannot translate it to formulas, or you can ask the user perhaps what is the right outcome on that input. And this was used by Sumit Gulwani and Sanjit and Atish Tiwari to, for example, synthesize simplifications of malware. The malware is a complex code that is difficult to translate, but the resulting synthesis is tiny, simple expressions. And of course, generate and test sometimes works well. If the space is small enough, that should not be underestimated. So with that, I want to stop here and say how generally synthesis, well, it depends on what you call program. Anything whose semantics you can specify and have some sort of interpreter for is in principle amenable to this sort of synthesis. Thank you.
We have time for perhaps a couple of questions and then take the rest offline.
Are you releasing Prosent?
Yes, in a couple of months. And if you want to see the demo, please see me during the break.
We hope to have a course in the fall, graduate course in building on Rosetta and extending it. So, I don't know, if you want to take the course remotely, you're welcome. I want to say that Armando, who wrote Sketch, is here in the room somewhere. Is Armando in the room? He's there in the back. So you can bother him with questions as well. He will love them.
So in your matrix transpose example, if the size of the matrix instead of being 16 was at all
So you could synthesize a matrix transpose that is parametric in the size of the matrix, but the code would look very different, right? That sketch itself would not work, of course, because that sketch is designed to unroll the loop specifically to the particular input. This is how these SIMD implementations work. So you would need to write it differently. If you want to have it parametric, the transpose would probably do optimization such as tiling the matrix into small chunks. And then the code would indeed have loops that iterate over tiles of a matrix. The tile would be computed from the size of the matrix. Then sort of n for size of the matrix would be a parameter that would be instantiated at synthesis time based on, again, the specific matrices that would drive the synthesis. But it would be different code. Tom.
You said at the beginning that you could only synthesize things with about 30 instructions long. Is there a hope for scalability by working bottom up? So if you have a larger problem, you synthesize an API, each of which takes up to 30 instructions. And then at the next level, you synthesize something that uses the functions of your API up to 30 uses of those API calls, and so on.
So I'll repeat the question, I clarify. So what I said at the beginning that we can synthesize of up to 30 instructions, that referred to the Denali result. So Denali, in their deductive way, they could do about 30 instructions compared to the super optimizers before. We could do more than 30 already by having a partial program which has a bunch of code specified. And what you synthesize then perhaps corresponds to the 30 instructions as well. So bigger synthesis by having a lot of it written, and you synthesize corner cases, if you will. But you ask about modular synthesis of some way, right? Synthesize smaller pieces and put them together. In principle, yes, the way we are actually approaching it now, you could say we do refinement, that we start actually not bottom up, but top down. You synthesize a program that calls a library function that is not specified, but what you synthesize at that point is perhaps an input-output pair specification for the library function. And then you go down and synthesize an implementation for the library function given those input-output pairs. You could do it bottom-up if those library functions were available to you and you express them in some way. Again, perhaps input-output pairs or some other transitive relations that summarize them, perhaps abstractly rather than concretely. I'm not sure that was done, but maybe Armando has been doing some work along these lines. There are, of course, all these systems that do synthesis on top of APIs, such as Prospector, Armando's Matchmaker, which try to understand libraries and stitch them together in some abstract syntax, such as types. And they sort of are something like that. But doing it in multiple levels, I'm not sure anybody has been doing it yet.
So I just have a final question, maybe to wrap up. So I just wanted to ask you that you mentioned this graduate student who took 1 day to come up with this matrix transpose and it took 5 minutes with the synthesizer. So let's say we gave him Concord or assembly solver. Do you think it would have gone down from a day to a few minutes even before we get to synthesis?
Well, how long did it take you to encode the formula for transposing code?
By hand?
By hand.
Well, it's an unfair question because I wrote the tool, but it only took me an hour.
It took, right. I think that people who know, say, Z3 and have written formulas by hand would probably take the same amount of time.
About
maybe
an hour,
less.
yeah.
Right. But having a compiler is, of course, useful. Right?
That's time to speak.